Mechanics is an area of science concerned with the behavior of physical bodies when subjected to forces or displacements, and the subsequent effects of the bodies on their environment. The scientific discipline has its origins in ancient Greece with the writings of Aristotle and Archimedes. During the early modern period, scientists such as Kepler, Galileo, Kepler, and Newton laid the foundation for what is now known as classical mechanics. It is a branch of classical physics that deals with particles that are either at rest or are moving with velocities significantly less than the speed of light. It can also be defined as a branch of science which deals with the motion of and forces on objects. Classical versus quantum mechanics. Historically, classical mechanics came first, while quantum mechanics is a comparatively recent invention. Classical mechanics originated with Isaac Newton's laws of motion in Principia Mathematica. Quantum mechanics was discovered in the early 20th century. Both are commonly held to constitute the most certain knowledge that exists about physical nature. Classical mechanics has especially often been viewed as a model for other so-called exact sciences. Essential in this respect is the relentless use of mathematics in theories, as well as the decisive role played by experiment in generating and testing them. Quantum mechanics is of a wider scope, as it encompasses classical mechanics as a sub-discipline which applies under certain restricted circumstances. According to the correspondence principle, there is no contradiction or conflict between the two subjects. Each simply pertains to specific situations. The correspondence principle states that the behavior of systems described by quantum theories reproduces classical physics in the limit of large quantum numbers. Quantum mechanics has superseded classical mechanics at the foundational level and is indispensable for the explanation and prediction of processes at molecular and atomic level. However, for macroscopic processes, classical mechanics is able to solve problems which are unmanageably difficult in quantum mechanics and hence remains useful and well used. Modern descriptions of such behavior begin with a careful definition of such quantities as displacement, time, velocity, acceleration, mass, and force. Until about 400 years ago, however, motion was explained from a very different point of view. For example, following the ideas of Greek philosopher and scientist Aristotle, scientists reasoned that a cannonball falls down because its natural position is in the Earth, the Sun, the Moon, and the stars travel in circles around the Earth because it is the nature of heavenly objects to travel in perfect circles. The father of science, Galileo, brought together the ideas of other great thinkers of his time and began to analyze motion in terms of distance traveled from some starting position and the time that it took. He showed that the speed of falling objects increases steadily during the time of their fall. This acceleration is the same for heavy objects as for light ones, provided air friction is discounted. The English mathematician and physicist Isaac Newton improved this analysis by defining force and mass and relating these to acceleration. For objects traveling at speeds close to the speed of light, Newton's laws were superseded by Albert Einstein's theory of relativity. For atomic and subatomic particles, Newton's laws were superseded by quantum theory. For everyday phenomena, however, Newton's three laws of motion remain the cornerstone of dynamics, which is the study of what causes motion. Relativistic versus Newtonian mechanics. In analogy to the distinction between quantum and classical mechanics, Einstein's general and special theories of relativity have expanded the scope of Newton and Galileo's formulation of mechanics. The differences between relativistic and Newtonian mechanics become significant and even dominant as the velocity of a massive body approaches the speed of light. For instance, in Newtonian mechanics, Newton's laws of motion specify that, whereas in relativistic mechanics and Lorentz transformations, which were first discovered by Hendrik Lorentz, General relativistic versus quantum. Relativistic corrections are also needed for quantum mechanics, although general relativity has not been integrated. The two theories remain incompatible, a hurdle which must be overcome in developing a theory of everything. History. Antiquity. The main theory of mechanics in antiquity was Aristotelian mechanics. A later developer in this tradition is Hipparchus. Medieval age. In the Middle Ages, Aristotle's theories were criticized and modified by a number of figures, beginning with John Philoponus in the 6th century. A central problem was that of projectile motion, which was discussed by Hipparchus and Philoponus. This led to the development of the theory of impetus by 14th-century French Jean Buridan, which developed into the modern theories of inertia, velocity, acceleration and momentum. This work and others was developed in 14th-century England by the Oxford calculators such as Thomas Bradwardine, who studied and formulated various laws regarding falling bodies. On the question of a body subject to a constant force, the 12th-century Jewish Arab Nathanael stated that constant force imparts constant acceleration, while the main properties are uniformly accelerated motion was worked out by the 14th-century Oxford calculators. Early modern age. Two central figures in the early modern age are Galileo Galilei and Isaac Newton. Galileo's final statement of his mechanics, particularly of falling bodies, is his two new sciences. Newton's 1687 Philosophiae Naturalis Principia Mathematica provided a detailed mathematical account of mechanics, using the newly developed mathematics of calculus and providing the basis of Newtonian mechanics. There is some dispute over priority of various ideas. Newton's Principia is certainly the seminal work and has been tremendously influential, and the systematic mathematics therein did not and could not have been stated earlier because calculus had not been developed. However, many of the ideas, particularly as pertain to inertia and falling bodies, had been developed and stated by earlier researchers, both the then recent Galileo and the less-known medieval predecessors. Precise credit is at times difficult or contentious because scientific language and standards of proof changed. So whether medieval statements are equivalent to modern statements or sufficient proof, or instead similar to modern statements and hypotheses, is often debatable. Modern age. Two main modern developments in mechanics are general relativity of Einstein and quantum mechanics, both developed in the 20th century based in part on earlier 19th century ideas. Types of mechanical bodies. The often used term body needs to stand for a wide assortment of objects, including particles, projectiles, spacecraft, stars, parts of machinery, parts of solids, parts of fluids, etc. Other distinctions between the various subdisciplines of mechanics concern the nature of the bodies being described. Particles are bodies with little internal structure, treated as mathematical points in classical mechanics. Rigid bodies have size and shape, but retain a simplicity close to that of the particle, adding just a few so-called degrees of freedom, such as orientation in space. Otherwise, bodies may be semi-rigid, i.e., elastic, or non-rigid, i.e., fluid. These subjects have both classical and quantum divisions of study. For instance, the motion of a spacecraft regarding its orbit and attitude is described by the relativistic theory of classical mechanics, while the analogous movements of an atomic nucleus are described by quantum mechanics. Subdisciplines in mechanics. The following are two lists of various subjects that are studied in mechanics. Note that there is also the theory of fields, which constitutes a separate discipline in physics, formally treated as distinct from mechanics, whether classical fields or quantum fields. But in actual practice, subjects belonging to mechanics and fields are closely interwoven. Thus, for instance, forces that act on particles are frequently derived from fields, and particles generate fields by acting as sources. In fact, in quantum mechanics, particles themselves are fields, as described theoretically by the wave function. Classical mechanics. The following are described as forming classical mechanics. Newtonian mechanics, the original theory of motion and forces. Analytical mechanics is a reformulation of Newtonian mechanics with an emphasis on system energy, rather than on forces. There are two main branches of analytical mechanics. Hamiltonian mechanics, a theoretical formalism, based on the principle of conservation of energy. Lagrangian mechanics, another theoretical formalism, based on the principle of the least action. Classical statistical mechanics generalizes ordinary classical mechanics to consider systems in an unknown state, often used to derive thermodynamic properties. Celestial mechanics, the motion of bodies in space. Planets, comets, stars, galaxies, etc. Astrodynamics, spacecraft navigation, etc. Solid mechanics, elasticity, the properties of deformable bodies. Fracture mechanics, acoustics, sound in solids, fluids and gases. Statics, semi-rigid bodies in mechanical equilibrium. Fluid mechanics, the motion of fluids. Soil mechanics, mechanical behavior of soils. Continuum mechanics, mechanics of continua. Hydraulics, mechanical properties of liquids. Fluid statics, liquids in equilibrium. Applied mechanics, or engineering mechanics. Biomechanics, solids, fluids, etc. In biology, biophysics, physical processes in living organisms. Relativistic or Einsteinian mechanics, universal gravitation. Quantum mechanics. The following are categorized as being part of quantum mechanics. Schrödinger wave mechanics, used to describe the motion of the wave function of a single particle. Matrix mechanics is an alternative formulation that allows considering systems with a finite dimensional state space. Quantum statistical mechanics generalizes ordinary quantum mechanics to consider systems in an unknown state, often used to derive thermodynamic properties. Particle physics, the motion, structure, and reactions of particles. Nuclear physics, the motion, structure, and reactions of nuclei. Condensed matter physics, quantum gases, solids, liquids, etc. Professional organizations. Applied Mechanics Division, American Society of Mechanical Engineers. Fluid Dynamics Division, American Physical Society. Society for Experimental Mechanics. Institution of Mechanical Engineers is the United Kingdom's qualifying body for mechanical engineers and has been the home of mechanical engineers for over 150 years. International Union of Theoretical and Applied Mechanics.